If you want to learn how to code this wormhole in Unity using C# code and some fun math, stick around. I'm going to show you how to do it. Okay, we're going to start with a new project here. It's a 3D project and I'll call it wormhole. And I'll click create. And then while that's creating, I'll pop over to my terminal and I'm going to CD down into the directory it creates and CD into the assets folder, and then I'm going to clone down my repo in that assets folder into a new folder called scripts. And then I'm going to go back to the root of the project and open it in VS Code just to make sure that my code's there. I see that my folders are there, and yeah, my code's there. So I'll go back to Unity, delete the camera, we don't need that. And I'm also going to change the name of the scene to something that makes more sense. Wormhole scene. And while I'm down here, I'll go ahead and create a new folder for the materials. And I'm just going to put one material in there, create material, and call it mesh material. And I'm going to go ahead and change the color of it now to blue. I like that more. And so now we can create the mesh. So right click, create empty object, call it mesh. And on that, add two components, the mesh filter and mesh renderer. And then on the renderer, expand that materials tab and drag over the material. And now we can create the other empty object, call it mesh maker. And on this object, we're going to drag over a couple scripts. So the first one's mesh maker. And yeah, sometimes you get this error. Just open up your code in VS Code, put a space in there and save it. That'll force it to recompile. And that should fix the error. So go back to it and drag it over again. It should work this time. It did. And then drag over the mesh drawer. And on the drawer, it needs the mesh object on the filter and renderer. There. Okay. So now we can click generate mesh, and the mesh generated successfully. I'm going to just change the directional light here just to get some more light. And we can zoom in on it. I'll turn it around. So one side is transparent, so I'm going to fix that. I'm going to add a double-sided shader that you can download from the Unity Asset Store. So just pop in here and grab this one from Syconia Studio or whatever. I've already downloaded it, so I'm just going to open up my package manager, go to my assets, and I'm going to import it from there. Just grab everything. That'll take just a second. Alright, and so now we can go to our material and change the shader on it to that new double-sided shader that we just downloaded. And now we should be able to see both sides. And we do. Okay, so now let's play with it a little bit. I'll zoom in here and I'll click on Mesh Maker over here so we can start messing with the parameters. So first I'll change the number of subdivisions in the splay. That's that curved part there. And I'll click on Auto Update so we can see it updating. So you can see I can change the splay to make it very few subdivisions and then slowly increase them, and it becomes a better and better curve. So we'll see in the code where those subdivisions come into play. And then the total change in U kind of controls how big the display is. So the smaller that number is, the kind of more acute the display will be, but if you make it bigger, it looks a little bit better in my opinion, because it curves more gently. Yeah, so you can just kind of put in whatever you want there. I like 10. Okay, let's mess with something else. So you can just get rid of the wormhole part altogether. So that's just creating the cylinder. And this is a polygonal cylinder, so it's composed of just cross-sectional polygons, and so that num sides controls how many sides there are in the polygon. So you can go all the way down to triangles, or you can go up to many sides that basically approximate a circle. And then you can also change the vertex radius. That changes kind of the size, the circumference of the cylinder. You can also change the length of the cylinder. And that's about it for this part. So let's jump into how I coded this. Okay, so I start with how do I code this left part, this cylinder. So essentially I draw, a polygon, and just for the sake of example, we'll start with the hexagon. And I take the point 1, 1 and I rotate it around this z-axis, I suppose. I rotate it around the z-axis by 60 degrees each time. And if it were a square, I'd rotate it by 90 degrees and so on. It's just 2 pi divided by n, where n is the number of sides in the polygon. But essentially what I get when I do this is I get all the vertices of a hexagon with its center at the origin and what I call its kind of vertex radius of 1. So it means that each of these vertexes is going to be 1 from the origin. Now, once I have those vertices, then I can start stacking the polygons. So what do I mean by stacking the polygons? This is a polygon over here that you can't see because it's into the this part is into the page here. So you're just seeing like one side of the polygon here. This would be another polygon here, and I'm stacking them. And so this, and I know I have it labeled X, my apologies, this is really the Z direction. So I'll take 2 polygons at different Z locations and I'll just connect up their vertices so that, both of them will connect their first vertices, and then both of them will connect their second vertices. And I'm going to make 2 triangles out of this. This forms a quad, so I'll make 2 triangles out of this, and then I'll go on to the next side. So if this were a hexagon, this would be, 1/6 of the work I'd have to do. Then I have to connect all the 5 other sides of this. But essentially, I'm just choosing 2 vertices on each polygon, and they'll be, if it's the first vertice on this one, it'll be the first vertice on the second one. Second vertice on the first one I'll match to the second vertice on the second one. And I'll just connect them all up and form these 2 triangles in a quad. That's what I mean when I say stack polygons. I'm stacking them in the Z direction. This is the code for rotating the point 1, 0 around the Z-axis to form all of the vertices of the polygon. It's right here in a class I call polygon. And you can see it's setting the unit vertices, and then when I get the vertices, I can pass in any vertex radius I want. So this is going to find all the vertices for a polygon with a vertex radius of 1, but I can pass in any vertex radius, and I just multiply all of the vertexes by that radius to get a polygon of any radius centered at the origin. And this is the code for stacking the polygons. So this is adding one of the triangles of the quad. This is adding the other triangle of the quad. These UVs deal with how you're stretching the texture onto your mesh. Essentially, there's 2 directions. The texture's 2D, and you're stretching this 2D texture onto your mesh by, for each vertice, you will say this vertice is this percent. This has gone this percent in this direction and this percent in the other direction, and you're essentially stretching the textures, and you're kind of pinning it down at each of the vertices, saying, okay, I should have used up 20% of the texture by now in this direction and like 40% in this other direction. If that doesn't make sense, this is not the video that you should learn that in, so I'm just going to leave it at that. This is stretching the texture on there. But you can see it's saying I1 and I2. That's those 2 different vertices I was just talking about. And the Z1 and Z2 are the 2 different Z coordinates of the polygons. And you can see that there are 2 different radiuses here because I can stack polygons of different radiuses. So that's how I create this splay part here, is I'm doing the exact same thing I'm doing with the rest of the cylinder, except I'm increasing the radius of the polygon each time. And so that kind of looks like this, where you've still got this polygon that's centered around 0, but the radius of the polygon over here is 2, kind of half of this distance. So the radius would be from the center out to 2. And then the radius of this one is 4, double that. But it still forms a quad, and you still stack them together with the exact same function. Now, the real question is, when you're stacking these polygons, well, how do I form that curve? How do I choose the radius and the z distance between the polygons such that I get a nice smooth curve like that? And so that's kind of the whole game here, is trying to find what radius and z distance between the polygons, what change in radius and change in z distance I need to form this nice smooth curve here. Okay, and so this is the problem. So here's the plane, these are the sides of the cylinder, and I'm trying to figure out what this kind of curve is here for the splay. And you can see that, well, whatever this curve is, its kind of derivative needs to match the cylinder at this point, and then it needs to match the plane at this point. And we can see that that's a 90-degree rotation. So essentially we need to find a curve that smoothly changes its derivative by 90 degrees. Okay, and so the easier way to do that is to rotate it 45 degrees. I'm not going to explain a whole lot about why this is easier, except to say the derivative here, if you're just trying to solve for this curve, the derivative here is infinity, and the derivative here is 0. But if you rotate it 45 degrees, the derivative here is positive 1, and the derivative here is negative 1. And that's still a 90-degree rotation from negative or positive 1 to negative 1. But obviously, it's working with plus and minus 1 is way easier than working with infinity and anything. Okay, so this is just the same problem rotated 45 degrees. And when we're rotating 45 degrees, I'm saying that we're rotating our coordinate system. So instead of talking about x and y, we're going to be talking about u and v. U and v are, so, if you rotate the x-axis up 45 degrees, you get this red u-axis. And then if you rotate the y-axis also 45 degrees in the same direction, you get this v-axis. And it's still a completely valid coordinate system. These are 90 degrees from one another and all that. They're just rotated 45 degrees. So instead of x and y, we're going to be talking about u and v. Okay, so this is the original splay curve in the x and y space. And if we rotate the problem 45 degrees, and my apologies, these are still labeled x and y. This should be u down here and v over here. But you get the point that it's a much simpler looking curve to deal with. And, obviously I've centered it a little bit. I've played with the centering because really all I'm interested in is finding, how quickly the derivative changes here and what the change in the v coordinate is corresponding to a given change in u. So this is the u axis. This vertical axis is the v axis. So I'm just interested in the change in u and the change in v. So it really doesn't matter whether I, move the parabola to the left or the right or up or down. If I'm just talking about the changes in each of the variables, then I can center it however I want. And so this is a nice, easy way to think of it, where it starts at a delta, at a v coordinate of 0, say, and it ends at a v coordinate of 0, and it travels a certain u distance. And you can kind of see that. So, if this, we're saying 45 degrees is the u and v. So if we look at this curve and we draw a 45-degree angle between it, the u is the only thing that's going to change. If v is oriented in this direction, then v just goes up for a moment, and then it comes right back down. Okay, here I've drawn the tangent lines as well, so we're starting off at a derivative of positive 1, and we're ending over here at a derivative of negative 1. So it's nice and symmetric in this rotated space. Okay, so this is the code for how to calculate the UV changes. So, for a given delta U, how much does delta V need to change in order to get this nice smooth curve? So this is the code for it, and this is the math for it. So essentially, since we're dealing with a parabola, the second derivative is constant. So let's say we divide the U distance we travel, and we get to pick that. In the code, I call it total change in U, but you get to vary that however you want, and that kind of controls the size of the splay. But let's say we, divided it in, we said the total change in U is 6, and we're going to divide it into these 6 equal pieces. And so what I'm going to try to find in code is, okay, what's the change in U at, this after this first delta U? And then what's the change in delta V after the second delta U? And third, and fourth, and fifth, and sixth. Okay, so delta U, and I'm going to call delta U the distance from the start to whichever piece we're talking about. So delta U sub 1, say, would be like the distance from here to there. Delta U sub 5 would be the distance from the start all the way over to 5. And so when I say, delta V corresponding to that delta U, I'm talking about the difference between the V coordinate at the start and the V coordinate at the end of that delta U. So that would be right about here. So this vertical distance. Okay, so the delta U is equal to I times basically the size of each of these little intervals. The total change in U, 6, divided by the number of divisions in this case would just be 1. So each of these little intervals here has a length of 1. And so if we're talking about the fifth segment, say I equals 5, then that has a length of 5. 5 times 1. That's all this is saying. And so I say here, given that the second derivative, given that we can calculate the second derivative, because we can calculate the second derivative as, okay, well, that's the total change in the derivative divided by the total change in U. So the ending derivative is -1, as we discussed. So that and the beginning derivative is +1. So the total change in the derivative is -2. And the total change in U is, like I said, we can set that to whatever we want. But if, for instance, we chose the total change in U to be 2, then the second derivative would be equal to -1. -2 divided by 2, which is -1. So I'm just arguing that we can calculate this easily, and we can also calculate the delta U's easily. So we can calculate the change in the first derivative. That's just going to be the second derivative times the change in U. And we can also calculate, therefore, the derivative itself, because we just add the change in the derivative to whatever it started at. And also because the second derivative is constant, because we're dealing with a parabola, we know that the average derivative is just whatever the derivative started at plus whatever it ended at divided by 2. So it's just the average of the start and ending derivatives for whatever interval we're talking about. And so therefore we can calculate delta V to be just the average derivative over the interval times the size of the interval. Okay, and you can think about that later if that doesn't make sense, but all I'm arguing here is that through some very simple calculations, we can calculate what the delta V is corresponding to any delta U we choose. And, we can choose it to be, we can divide the total distance into, first of all, we can pick the entire distance, the total change in U, and then we can divide it into any number of pieces, however many pieces we want. And however we decide to do that, we can always calculate the delta V at the end of each of those intervals corresponding to that delta U. So we've solved for the curve here. but we've solved for that curve in UV space. So remember that these axes are rotated relative to the space we started in. So now we just got to rotate them back, and that's what this code's doing. It's essentially just just doing a 45-degree rotation in the opposite way that we originally did. So we rotated upwards to get to the UV axes. Now we're going to rotate back down to get back to the X and Y axes. And that's what this page is really discussing. So you essentially, if I have some delta U right here, I can break that down and I can see what the corresponding change in X and Y is for that delta U. And I can do the same thing for a delta V. I can get a corresponding change, and you see a negative sign. All these are positive except for this one. And that's because if I change V, if I increase V, then the component of V in the X direction, that's actually decreasing X. That's negative X. So as I increase V, I'm decreasing X. So that's why that negative sign is there. So you can think about that later. This is a right triangle. I'm getting it from right here. So this is a right triangle, and these are both 45-degree angles. This one's a 45-degree angle because we rotated by 45 degrees, and this one's 45 degrees because all these angles have to add up to 180 in a triangle. Okay, so the math works out if you use the Pythagorean theorem to, delta U splits evenly and contributes to a delta X and a delta Y, and the magnitude of it is just delta U divided by the square root of 2. And same thing over here except with the negative sign. So if you put it together, then delta X is equal to the change in U divided by square root of 2 minus the change in V divided by square root of 2, blah, blah, blah. And again, this is just a rotation of 45 degrees. So all this is saying is now that we've gotten our delta U's and delta V's, we can easily translate them to delta X's and delta Y's for the splay curve. Okay, so now the only part left is to explain kind of how do we take these X and Y changes and create our splay from that? Like, how do we translate that back into our original problem? So here's our original problem. The X coordinate is in the horizontal direction, the Y coordinate in the vertical. So the changes in X's will correspond to the changes in kind of the radiuses, the vertex radiuses of the polygons. And then the changes in Y that we calculated will correspond to changes in the Z direction. Because like I was saying, every time we're stacking these polygons, we're stacking one polygon at one Z coordinate and then another polygon on top of it at a larger Z coordinate. And the way I've coded it is the end of the cylinder occurs at Z equals 0. So sorry, this like these numbers on the side, just ignore those, and the label of the axis, ignore that as well, because this is really an X versus Z drawing here. So the end of the cylinder occurs at Z equals 0, and so we're going to go up from there, and so our delta Y's that we get from our splay calculation that we just made here are going to be how much up we go in the Z direction, and then the delta X's that we just calculated are going to be how much wider does the radius of the polygons get. Okay, and then that's what this code does here. So you can see it grabs the XY changes. So this is a vector 2 here, this splay point. And I just say, okay, the next radius is the starting radius plus whatever the X change is. Because like I said, those X and Y changes are from the very beginning. So when we were talking about this, I was saying that I've defined the intervals to be from whatever your starting point is up until that point. Well, in terms of radius, our starting point is the radius of the cylinder, the original radius of the cylinder. And then in terms of Z, the starting point is the Z coordinate of the end of the cylinder, which is actually 0, the way I've coded it. So the next Z coordinate will just be the Y coordinate, the Y change given by the splay data plus 0. Okay, and then we stack those polygons. So we've got a slightly larger polygon here that we're stacking onto the previous polygon, and it's at a slightly larger Z value. And then at the end, the way that I create the plane is just to stack another polygon on the other one at the same Z coordinate. So essentially the quads, go out horizontally, and I just set the vertex of the last one that I stacked to be, this factor of 10 times larger than the other radius. So that just kind of forms a polygonal plane, if you will. And so that's all the theory of the code that you need to understand to get through the code. And now I'll take you through just kind of how the code invocations work, how the call stack in the code works. Okay, briefly, this generate mesh button, when you click it, it's going to go into this function. And so when you click it, it'll actually execute this line here. If auto update is checked, then anytime you make an update in there, it's also going to call the same function. So let's pop into that function. That function says, set the debug mode enabled. So debug mode enabled just controls whether you're saving data, either printing it to the screen or saving it to a CSV. But it'll call this function. This function basically calls everything else. So first it gets the texture, then it creates the cylinder part of it, and then if you've got add wormhole checked, so that is this check mark here. So if you've got it checked, it will pop in here and it will decide display data, those X and Y changes that we just went over, and it will use that display data to generate the polygonal cylinder splay, so that kind of curved part that we just went over, the splay. And we've gone over the key functions in those, so I'm not going to go over that. I just kind of wanted to, and then it just draws the mesh, which is a very simple function. So I just wanted to kind of mainly show you where the code starts, and you can kind of follow it through. And we've gone through, like I said, the key functions in these files. They're not very big. They're pretty simple. We've gone through the hard parts. So that's all of it. That's it. Thanks for watching.